Picture the final moments of a dying star, a colossal explosion that should mark the end of its story. But what if death isn't the end? What if, against all odds, that star claws its way back from the cosmic grave, defying the very laws that govern the universe? This isn't science fiction. It's the chilling reality of zombie stars, celestial phantoms that refuse to stay dead. These cosmic anomalies aren't just eerie curiosities. They're rewriting the rules of astrophysics, challenging everything we thought we knew about how stars live, die, and sometimes return. Think about the sheer audacity of a star cheating death. When most stars die, they fade into black holes or cold, dense husks. But zombie stars, they're the ultimate cosmic rebels. Some reignite in violent outbursts, blasting their way back to life. Others lurk in the shadows, feeding on nearby matter like celestial vampires. And then there are the ones that collapse so violently, they tear the fabric of space-time itself, sending ripples across the universe. These aren't just dead stars. They're cosmic time bombs, ticking away in the darkness, holding secrets that could unlock the mysteries of dark matter, gravitational waves, and even the fate of our own sun. So how does a star rise from the dead? What twisted physics allows these celestial zombies to exist? And what happens when we peer into their glowing remnants, searching for answers? Buckle up, because we're about to dive into one of space's most mind-bending phenomena. From white dwarfs that explode like cosmic to neutron stars spinning faster than a blender on overdrive, the universe is stranger and more alive than we ever imagined. This isn't just a story about stars. It's a story about how the universe defies death itself. And by the end of this journey, you'll never look at the night sky the same way again. Stars don't just flicker out like candles. They go out with a bang, a whimper, or sometimes a shocking second act. Take a massive star, for instance. After burning bright for millions or even billions of years, it exhausts its nuclear fuel, triggering a catastrophic collapse. For most, this is the end. The core crushes itself into a neutron star or vanishes into a black hole, while the outer layers blast away in a supernova, a final, dazzling farewell. But here, where things get weird, some stars don't stay gone. They find a way back, like cosmic phoenixes rising from their own ashes. The key lies in their death throes. When a star like our sun dies, it sheds its outer layers, leaving behind a dense, Earth-sized ember called a white dwarf. Normally, that's where the story ends, a slow fade into darkness. But if that white dwarf has a companion star, things get interesting. It can siphon material from its neighbor, piling it onto its surface until the pressure and heat reignite nuclear fusion in a violent explosion. Astronomers call this a nova, a sudden, brilliant rebirth. And in rare cases, the entire white dwarf detonates in a type supernova, outshining entire galaxies. That's not just cheating death, it's going out in a blaze of glory twice. Then there are neutron stars, the collapsed cores of once massive stars, so dense a teaspoon of their material would weigh 1 billion tons. Some of these spin at dizzying speeds, emitting beams of radiation that sweep across space like lighthouse beacons. We call them pulsars, and they're essentially stellar zombies, dead but still eerily active. But even these can get a second wind. If a neutron star orbits another star, it can strip away material, spinning faster and faster until it becomes a millisecond pulsar, one of the most precise cosmic clocks in the universe. It's like a cosmic vampire, feeding to stay unnaturally youthful. And then there's the strangest resurrection of all, the Magnetar. Imagine a neutron star with a magnetic field so powerful it could wipe data from every credit card on Earth from halfway across the galaxy. These monsters occasionally unleash violent ruptures on their surfaces that release bursts of energy so intense they briefly outshine every other object in the Milky Way. It's as if the star's corpse is twitching back to life, sending shockwaves through the cosmos. So what does this mean for our understanding of stellar life cycles? It turns out death in the universe isn't always permanent. With the right conditions, a companion star, a massive magnetic field, or just sheer cosmic luck, a star can defy expectations, rewriting its own ending. And that's what makes these zombie stars so fascinating. They're not just freaks of nature, they're cosmic laboratories, showing us how matter behaves under the most extreme conditions imaginable. Every time we spot one of these undead stars, we're glimpsing the universe's hidden rules, written in light, gravity, and the relentless will to survive. Zombie stars are the universe's ultimate rule breakers, celestial objects that refuse to fade quietly into the cosmic night. They're not alive in the traditional sense, yet they're far from dead. Picture a white dwarf, the smoldering core of a star like our sun, left to cool over eons. Normally, that's where its story would end. But give it a companion star, and suddenly it's stealing material, building up pressure until, boom, it erupts in a nova or even a cataclysmic supernova. That's not just a second chance, it's a cosmic encore, defying the very definition of stellar death. Then there are neutron stars, the densest objects in the universe outside black holes. These aren't just cold, inert relics. Many of them spin hundreds of times per second, shooting beams of radiation across space like interstellar lighthouses. Some, called Magnetars, wield magnetic fields so strong they could warp atoms from thousands of light years away. When these stars crack under the strain, releasing bursts of energy, it's like watching a corpse suddenly sit up and scream. And let's not forget black holes, the ultimate cosmic graves. Even these seemingly bottomless pits can spit out radiation, thanks to the frenzied particles swirling around their event horizons. In a way, they're the most paradoxical zombies of all, swallowing everything nearby while simultaneously belching out energy, as if death itself has a heartbeat. What ties these bizarre objects together? Extreme physics. Gravity so intense it warps space-time. Magnetic fields that could shred planets. Matter crushed into states so dense they defy earthly logic. Zombie stars exist because the universe, at its most extreme, doesn't play by the rules we're used to. They're not just oddities, they're windows into the most violent, high-energy processes in existence. Every flicker, every pulse, every explosion is a clue, helping us unravel the secrets of matter, energy, and the very fabric of reality. So when we stare into the abyss, sometimes, against all odds, the abyss stares back with a flickering, undead glow. White dwarfs are the universe's quietest ghosts until they're not. These Earth-sized embers are all that remain of stars like our sun after they've burned through their fuel and shed their outer layers. Left alone, a white dwarf will slowly cool over billions of years, fading into a cold, dark husk. But place it near a companion star and the story takes a twisted turn. Like cosmic thieves, some white dwarfs siphon material from their neighbors, pulling gas and dust onto their surfaces. Over time, the stolen matter piles up, compressing under unimaginable gravity until suddenly it ignites. The result, a runaway thermonuclear explosion so bright it can outshine entire galaxies. This isn't just a stellar flare-up, it's a full-blown resurrection. Astronomers call these events type supernovae, and they're among the most powerful explosions in the universe. What makes them so bizarre is their consistency. Unlike other supernovae, which vary wildly in brightness, type explosions always release roughly the same amount of energy. That predictability makes them cosmic measuring sticks, allowing scientists to gauge distances across the universe. In fact, it was observations of these undead stars that first revealed the shocking truth. The universe isn't just expanding, it's accelerating. But the real mystery lies in how these white dwarfs cheat death in the first place. Normally, a star's life ends when it can no longer fuse atoms in its core. A white dwarf is essentially a stellar corpse. Its atoms packed so tightly they form a bizarre quantum soup called degenerate matter. Yet when enough fresh hydrogen or helium rains down from a companion star, the dwarf's surface temperature skyrockets, reigniting fusion in a violent chain reaction. For a brief, brilliant moment, the dead star lives again, before tearing itself apart in a final, apocalyptic blast. The aftermath is just as fascinating. These explosions forge heavy elements like iron, gold, and platinum, scattering them across space. Every time you wear a gold ring or glance at a stainless steel appliance, you're holding remnants of a white dwarf's last defiant act. These zombie stars don't just die twice, they reshape the cosmos in their wake, seeding future generations of stars, planets, and even life itself. So the next time you look up at the night sky, remember, some of those faint, steady points of light might not be stars at all. They could be white dwarfs biding their time, waiting for the chance to steal, ignite, and explode, proving that in the universe, even death isn't always the end. Type supernovae are the universe's ultimate cosmic comeback, stellar zombies that refuse to fade quietly into the dark. These explosions aren't just bright, they're blinding, capable of outshining every star in their host galaxy combined. But what makes them truly extraordinary isn't just their brilliance, it's their precision. Unlike other supernovae, which flare up with unpredictable intensity, type detonations follow a near-identical script. Each one releases almost the same amount of energy, like cosmic clockwork. This eerie consistency turns them into celestial yardsticks, helping astronomers measure the vast distances between galaxies. So how does a dead star pull off such a precise, violent rebirth? The secret lies in a deadly tango between two stars. Imagine a white dwarf, the dense, Earth-sized core of a star like our Sun, locked in orbit with a companion, perhaps a red giant or another white dwarf. Over time, the dwarf's gravity greedily steals material from its partner, funneling hydrogen or helium onto its surface. At first, this stolen matter just sits there, compressed under unimaginable pressure. But as the pile grows, temperatures skyrocket. Suddenly, the conditions become perfect for nuclear fusion to reignite, not in the star's core, where it once burned, but explosively across its surface. The result is a runaway thermonuclear chain reaction. In less than a second, the entire white dwarf becomes a bomb, its carbon and oxygen atoms fusing into heavier elements like iron and nickel. The explosion tears the star apart, scattering its guts across space in a fireball visible billions of light years away. But here's the twist, because all type supernovae detonate at roughly the same mass threshold, about 1.4 times the mass of our Sun, their explosions are nearly identical in brightness. That's why astronomers call them standard candles. They're the universe's built-in measuring tape, helping us map the cosmos. Yet mysteries remain. What happens if the white dwarf's companion isn't a star but another white dwarf? Some theories suggest these zombie stars might collide, merging into a single supermassive object that instantly triggers a supernova. Others propose that the theft of matter isn't always steady. Sometimes it's a violent, chaotic process. And then there's the question of rogue white dwarfs drifting alone through space. Could they somehow resurrect themselves without a partner? The answers could rewrite our understanding of stellar death and life. What's undeniable is the legacy of these explosions. Every type supernova seeds the cosmos with heavy elements, the building blocks of planets and life. The iron in your blood, the gold in your jewelry, even the silicon in your phone, they all owe their existence to stars that died not once but twice. So the next time you hear about a distant supernova, remember, it might not just be a star's death knell, it could be its encore. Neutron stars are nature's most extreme tombstones, stellar corpses so dense they defy common sense. Imagine cramming the entire mass of our Sun into a sphere no wider than Manhattan. The result, a teaspoon of neutron star material would weigh more than Mount Everest. But these cosmic remnants aren't just inert relics. Some of them pulse with eerie regularity, sending beams of radiation slicing through the cosmos like a lighthouse cutting through fog. Astronomers call them pulsars, and they're the universe's most precise timekeepers, spinning with such consistency that their rhythmic flashes rival atomic clocks. Then there are the Magnetars, neutron stars with a terrifying twist. Their magnetic fields are a quadrillion times stronger than Earth's, so powerful they could strip the electrons from atoms thousands of miles away. If a magnetar lurked halfway between Earth and the Moon, its magnetic grip would erase every credit card on our planet. These monsters occasionally unleash violent fractures in their crust that release gamma-ray bursts brighter than 100 suns. It's as if the star's corpse is convulsing, sending shockwaves through the fabric of space-time. What makes these undead stars so fascinating isn't just their bizarre properties, it's what they teach us about the limits of physics. Neutron stars are essentially giant atomic nuclei, their matter crushed into exotic states we can't replicate on Earth. Protons and electrons fuse into neutrons, creating a quantum soup where the rules of gravity and quantum mechanics collide. Some theories suggest their cores might harbor even stranger substances, free-floating quarks or hyperons, particles that could rewrite our understanding of matter itself. Pulsars, with their clockwork precision, serve as cosmic laboratories. By tracking their pulses, scientists have confirmed theory of general relativity, detected gravitational waves, and even mapped the invisible halo of dark matter surrounding our galaxy. Magnetars, meanwhile, offer glimpses into the universe's most violent forces. Their eruptions mimic the birth cries of black holes, helping us decode the chaotic moments when space itself tears apart. Yet for all their ferocity, neutron stars have a poetic side. Their very existence is a testament to balance, a star's gravity crushing inward, held at bay only by the subatomic forces between neutrons. It's a delicate dance between destruction and survival, played out in the hearts of these undead giants. And every flicker, every quake, every pulse is a message, a reminder that even in death, stars still have stories to tell. Magnetars take cosmic violence to an entirely new level. These aren't just dead stars, they're celestial berserkers. Picture a neutron star, already one of the densest objects in existence, then crank its magnetic field up to ludicrous levels. We're talking about forces so intense they could atomize a human from 1,000 miles away. If you held a magnetar as close as the Moon, its magnetic grip would warp the electrons in your body before you even had time to blink. But what makes these monsters truly terrifying isn't just their strength, it's how they unleash it. When a magnetar's unimaginably powerful magnetic field gets tangled, it twists the star's solid crust. Yes, these things have a crust, like a cosmic rubber band stretched to its limit. Eventually, that tension snaps. The result, a seismic event so violent it ripples through spacetime itself. These aren't gentle tremors. A single crack in a magnetar's surface can release more energy than our sun emits in 100,000 years, all in a fraction of a second. The aftermath. A blast of X-rays and gamma rays so bright it temporarily outshines every other source in the galaxy. And here, where things get even stranger. Some scientists suspect magnetars might be behind one of the universe's most puzzling signals, fast radio bursts. These mysterious blips of energy last just milliseconds, yet they pack the punch of hundreds of millions of suns. For years, their origins were a total enigma. Were they alien signals, colliding black holes, or something even weirder? Then, in 2020, astronomers caught a magnetar in our own galaxy, firing off a burst that matched the profile of a fast radio burst. Suddenly, the pieces started falling into place. But magnetars don't just solve mysteries, they create them. Take soft gamma repeaters, a special class of magnetars that erupt unpredictably, like cosmic geysers of radiation. No one fully understands why they flare up when they do, or how their magnetic fields grow so absurdly strong in the first place. Some theories suggest these zombies are born spinning impossibly fast, their magnetic fields amplified by the chaotic dynamo of their infancy. Others propose they're the remnants of stars that barely avoided collapsing into black holes, leaving behind a core so unstable it crackles with pent-up energy. What's undeniable is their role as cosmic crucibles. The conditions around a magnetar are so extreme they warp the very fabric of quantum physics. Electrons don't just orbit atoms here, they're stretched into needle-thin spirals by the magnetic field. Light itself bends in weird ways, trapped in a maze of forces beyond anything we can replicate on Earth. Studying these undead stars isn't just about cataloging celestial oddities. It's about probing the outer limits of reality, where matter, energy, and spacetime itself behave in ways that defy intuition. So the next time you hear about a distant flash of gamma rays or a puzzling radio burst, remember, it might not be a dying star's last gasp. It could be a magnetar screaming into the void, reminding us that even in death, the universe is anything but quiet. Black holes don't just swallow light, they bend the rules of existence itself. These cosmic monsters are often called the universe's ultimate endpoints, where gravity wins and nothing escapes. But calling them dead couldn't be further from the truth. A black hole is more like a cosmic vampire, feeding on anything unlucky enough to wander too close. Picture a star ripped apart by tidal forces, its gas spiraling into the abyss at nearly the speed of light, heating up until it glows brighter than 1,000 suns. That's not a grave, it's a dynamo of destruction and rebirth. Take quasars, for example. These dazzling beacons are powered by supermassive black holes at the hearts of galaxies, gorging on so much material that their accretion disks outshine every star around them. The energy they release can sculpt entire galaxies, shutting down star formation or igniting it anew. It's as if the black hole isn't just a predator, it's a cosmic architect, reshaping its surroundings with the leftovers of its meals. Then there's Hawking radiation, the ghostly whisper that hints at a black hole's slow evaporation. According to quantum theory, pairs of particles flicker in and out of existence near the event horizon. Sometimes one falls in while the other escapes, stealing a tiny bit of the black hole's mass. Over trillions of years, this process could cause even the mightiest black hole to fade away. But here's the twist. As they shrink, they heat up, potentially ending their lives in a final, fiery explosion. That's not just death, it's a transformation, a cosmic recycling of energy on scales we can barely fathom. And what about the singularity at a black hole's core? Our laws of physics break down there, leaving open wild possibilities. Could it be a gateway to another universe? A knot of spacetime so twisted it births something entirely new. Some theories suggest that under the right conditions, a black hole's collapse might reverse, birthing a white hole, a region where matter and energy erupt outward instead of vanishing inward. Imagine a cosmic reset button, where death flips into creation. So while black holes might seem like the end of the story, they're more like ellipses, pauses in a narrative far stranger than we've yet imagined. From devouring stars to leaking quantum whispers, these undead giants prove that in the universe, even the darkest endings can spark new beginnings. And that's the most haunting truth of all. In the cosmos, nothing truly dies, it just changes form. Quantum resurrection isn't just science fiction, it's a radical reimagining of how the universe handles death. Picture a black hole, the ultimate cosmic predator, slowly evaporating over eons due to Hawking radiation. This isn't some violent explosion, it's a whisper of particles escaping the black hole's grip, each one carrying away a tiny fraction of its mass. Given enough time, trillions upon trillions of years, even the mightiest black hole could fade into nothingness. But what if it doesn't just vanish? Some theories suggest it might leave behind a faint, enigmatic remnant, a ghostly fingerprint of all it once consumed. This idea ties into one of physics' greatest puzzles, the information paradox. According to quantum mechanics, information, the fundamental blueprint of every particle, every atom, can never truly be destroyed. Yet black holes seem to violate this rule, swallowing stars, planets, and light without leaving a trace. Or do they? Some physicists argue that the information isn't lost. It's scrambled like a cosmic shredder and could eventually re-emerge in some unrecognizable form. Imagine tossing a book into a fire, only for the ashes to rearrange themselves centuries later into a new story. That's the level of weirdness we're dealing with here. Implications are staggering. If black holes can preserve and eventually release information, even in a distorted state, then the universe might operate like an endless recycling plant. Matter isn't destroyed, it's transformed, rewritten, and redistributed. This could mean that every atom in your body, every speck of dust in the cosmos, has lived countless lives across billions of years, passing through stars, black holes, and who knows what else. It's a poetic thought. Death isn't an end, but a doorway. Even more mind-bending is the idea that the universe itself might be part of this cycle. Some models suggest that the remnants of evaporated black holes could seed new universes, birthing entirely new realities from the ashes of the old. It's a cosmic version of the Phoenix myth: collapse, rebirth, repeat. While these theories remain speculative, they force us to confront the possibility that the universe isn't just a one-way street toward heat-death. There might be hidden exits, secret loops, and resurrection baked into the very fabric of reality. So what does this mean for zombie stars and other celestial undead? They might be just one piece of a much larger puzzle, a universe where nothing truly dies, only changes form. Whether through white dwarfs stealing life from companions, neutron stars pulsing with unnatural vigor, or black holes leaking quantum whispers, the cosmos seems obsessed with cheating death. And if physicists are right, even the darkest corners of space might hold the seeds of something new. After all, in a universe this strange, why should death have the final word? Dark matter might be the universe's ultimate ghost, invisible, elusive, yet holding galaxies together with its gravitational grip. But what if this mysterious substance isn't just lurking in the voids of space? What if it's hiding inside stars, subtly rewriting their fates? Some scientists speculate that dark matter could be the hidden puppeteer behind certain zombie stars, altering their life cycles in ways we're only beginning to unravel. Imagine a dense neutron star, its core packed with neutrons under unimaginable pressure. Now picture dark matter particles, hypothetical entities like WIMPs, weakly interacting massive particles drifting through space. If these particles collide with the neutron star, they could get trapped by its gravity, sinking to the core. Over time, this buildup could ignite exotic nuclear reactions, releasing energy that might explain sudden bursts of activity from these supposedly dead stars. It's like pouring gasoline on embers. Dark matter could be the unseen fuel reigniting cosmic corpses. The idea gets even stranger with white dwarfs. These stellar remnants are already ticking time bombs, waiting for a companion star to trigger their explosive rebirth. But what if dark matter plays a role in their detonations? Some theories suggest that if enough dark matter accumulates inside a white dwarf, it could provide extra heat, destabilizing the star and causing it to explode prematurely, without needing a stellar partner. This would rewrite the textbook explanation for type supernovae, turning dark matter into a cosmic arsonist, silently setting the stage for stellar resurrections. Then there's the mystery of certain pulsars, neutron stars that spin with eerie precision, suddenly glitching, their rhythms faltering for no apparent reason. Could dark matter be the culprit? If pockets of dark matter lurk inside these stars, their gravitational tugs might disrupt the star's rotation, like an invisible hand nudging a spinning top. These glitches could be the smoking gun, hinting at dark matter's subtle but profound influence on the undead stars we observe. Of course, this is all speculative. Dark matter remains one of the universe's greatest unsolved puzzles. We've never directly detected it, and its interactions with normal matter are frustratingly faint. Yet the possibility that it could breathe life into dead stars is too tantalizing to ignore. If proven true, it would mean dark matter isn't just a passive scaffold for galaxies. It's an active player in stellar evolution, shaping the lives and afterlives of stars in ways we never anticipated. So as we scan the skies for zombie stars, white dwarfs flaring back to life, neutron stars spinning erratically, or supernovae defying explanation, We might also be hunting for dark matter's fingerprints. Every anomaly, every unexpected burst of energy could be a clue pointing to this invisible force's role in the cosmic cycle of death and rebirth. And if we're right, the universe's most elusive substance might be the very thing keeping its dead stars alive. Gravitational waves are the universe's hidden messengers, carrying secrets from the most violent events in the cosmos. When two neutron stars, ultra-dense remnants of dead stars, spiral into each other, their collision doesn't just light up the sky. It shakes the very fabric of spacetime, sending out ripples that travel across billions of light years. These waves, predicted by over a century ago, were first detected in 2015, opening a new window into the afterlife of stars. But what makes them so special? They're not just cosmic echoes, they're forensic evidence, revealing details about the undead stars that created them. Take the historic detection in 2017, when scientists caught gravitational waves from two neutron stars colliding. The event, dubbed GW170817, wasn't just a ripple in space-time. It was a full-blown cosmic spectacle. Telescopes around the world swiveled to catch the aftermath. An explosion so powerful it forged heavy elements like gold and platinum in seconds. The gravitational waves told the story first, how the stars danced closer, how their crushing gravity distorted spacetime, and finally, how they merged into either a heavier neutron star or a black hole. It was like listening to the last, desperate heartbeat of two stellar corpses before they became something new. But gravitational waves don't just show us collisions. They can also expose the inner workings of lone neutron stars, especially those with slight deformities. Picture a pulsar spinning hundreds of times per second, its surface not perfectly smooth but dotted with microscopic mountains, tiny bumps no taller than a few millimeters. Even these minuscule imperfections, whipped around at near-light speeds, can generate gravitational waves. Detecting these faint signals would let scientists map the star's surface in unprecedented detail, like using ripples in a pond to reconstruct the shape of the pebble that made them. Then there's the eerie phenomenon of neutron star quakes. When a magnetar's crust cracks under the strain of its own magnetic field, the resulting doesn't just release radiation, it can also emit a burst of gravitational waves. These tremors carry clues about the star's interior, hinting at whether its core is a soup of free quarks or a crystalline lattice of neutrons. It's like putting a stethoscope to a zombie star's chest, listening for the whispers of its alien physics. And the future holds even more promise. Next-generation observatories, like the Laser Interferometer Space Antenna, LISA, will hunt for gravitational waves from supermassive black holes and even white dwarf binaries. Imagine catching the moment a white dwarf steals enough mass from its companion to go supernova, not through light, but through the warping of spacetime itself. Or detecting the low-frequency hum of two black holes circling each other for millions of years before their final merger. These signals could reveal how often stars cheat death, and what strange forms they take in their second lives. Gravitational waves are more than just cosmic curiosities, they're reshaping our understanding of stellar resurrection. Every ripple carries a story of collisions, quakes, and the unseen forces that animate the universe's undead. And as our detectors grow more sensitive, we're not just observing these events, we're stepping into a new era of astronomy, where spacetime itself is the messenger, and the dead stars still have plenty to say. Binary systems are the ultimate cosmic power couples, stellar duos locked in a gravitational embrace that can turn death into a spectacular encore. When one star in a pair dies, it doesn't always fade quietly into the void. Instead, its surviving companion can become a lifeline fueling resurrection in ways that defy the ordinary rules of stellar demise. Picture a white dwarf, the smoldering core of a dead star, orbiting a bloated red giant. As the giant sheds its outer layers, the dwarf siphons off that material, piling it onto its surface until the pressure triggers a thermonuclear explosion. This isn't just a one-time event. It's a cycle of death and rebirth, with some binary systems erupting in recurrent novae every few decades, like cosmic time bombs set on repeat. But the real drama unfolds when the zombie star isn't just stealing matter, it's consuming its partner whole. In rare cases, a neutron star or black hole can spiral into the core of its companion, creating a bizarre hybrid known as an object. Imagine a red supergiant, its outer layers billowing into space, hiding a neutron star at its heart like a cosmic Russian nesting doll. The neutron star's gravity churns the surrounding gas, altering the giant's nuclear reactions and producing exotic elements rarely seen in nature. These objects are so strange that for decades, they existed only in theory, until astronomers spotted a handful of candidates, their chemical fingerprints betraying the hidden monster within. The stakes get even higher when both stars in a binary system are destined for undead afterlives. Take two white dwarfs locked in a slow death spiral. As they lose energy to gravitational waves, their orbits shrink until catastrophe. They collide, merging into a single object so massive it ignites a type supernova, obliterating both stars in a blaze of glory. These explosions are so uniform they're used as cosmic measuring tapes, yet their origins, whether from solo white dwarfs stealing mass or binary mergers, remain one of astrophysics' hottest debates. Then there's the case of X-ray binaries, where a neutron star or black hole feasts on its companion so voraciously that the stolen matter forms a swirling accretion disk, glowing with X-rays as it's devoured. Some of these systems flare unpredictably, as if the dead star is flickering back to life with each gulp of stellar material. Others, called shoot-out jets of particles at near-light speed, mimicking the behavior of their supermassive cousins in galactic cores. It's a haunting spectacle, a corpse, animated by its partner's sacrifice, beaming radiation across the cosmos like a zombie with a pulse. So how common are these undead duos? The Milky Way alone could harbor millions of binary systems with white dwarfs, neutron stars, or black holes, each a potential stage for stellar resurrection. Some lurk quietly, their interactions too faint to notice. Others announce themselves with bursts of light, gravitational waves, or bizarre chemical signatures. What's clear is that binary systems aren't just cosmic curiosities. They're crucibles of reinvention where stars cheat death, rewrite their fates, and prove that in the universe, even the end can be a beginning in disguise. Objects are cosmic Russian nesting dolls gone wrong, a neutron star buried deep inside the bloated belly of a red giant, like a ticking time bomb wrapped in stellar flesh. This isn't just a dead star. It's a stellar parasite, its immense gravity churning the giant's core like a spoon in a nuclear soup. The result, a freakish hybrid that defies every textbook on stellar evolution. Normally, red giants fuse hydrogen into helium in their outer shells, but with a neutron star stirring the pot, everything changes. The intruder's gravity disrupts normal fusion, forcing the giant to cook up exotic elements like rubidium, lithium, and molybdenum, rare ingredients that leave ghostly fingerprints in the star's light. For decades, these objects were pure theory, dreamed up by physicists Kip and Anna in the 1970s. Then, in 2014, astronomers spotted a red giant named HV 2112 in the small cloud with a chemical cocktail unlike any other star. Its atmosphere was laced with excess lithium and molybdenum, exactly the bizarre signature an object would leave behind. Was this the smoking gun? Maybe. But without catching the neutron star's X-ray pulse or gravitational whisper, the discovery remains tantalizingly unconfirmed. What makes these hybrids so unsettling is their inevitable fate. Eventually, the red giant will shed its outer layers, exposing the neutron star to space. If the dupe survives long enough, they might spiral closer, merging in a cataclysm that could unleash a gamma-ray burst or even birth a black hole. It's a slow-motion stellar murder-suicide, hidden behind curtains of gas and dust. And if objects exist, what other undead hybrids might be lurking in the cosmic shadows? Imagine a black hole orbiting inside a supergiant, invisibly gnawing at its host's core, or a white dwarf and neutron star locked in a deadly embrace, trading mass until one triggers the other's destruction. The universe's rulebook is filled with blank pages, and zombie stars are scribbling in the margins. Every time we think we've seen it all, the cosmos whispers, "Just wait." The weirdest resurrections are still out there, waiting to be found. Failed supernovae are the universe's greatest disappearing acts, stars that vanish without a trace, leaving behind nothing but a black hole and a trail of unanswered questions. Imagine a massive star, 20 times heavier than our sun, reaching the end of its life. You'd expect a spectacular supernova, a blinding flash visible across galaxies. But sometimes that explosion never comes. Instead, the star implodes silently, collapsing straight into a black hole as if the universe hit the mute button on its death. Astronomers call these events failed supernovae, and they're some of the most perplexing mysteries in modern astrophysics. The first clue something was amiss came from a star named N6942. In 2008, it was there, shining brightly. By 2009, it had vanished. No explosion, no fading ember, just gone. Telescopes scoured the spot, finding only a faint infrared glow, likely from dust heated by a hidden black hole's gravity. It was as if the star had been erased, its death certificate signed in invisible ink. Since then, a handful of other stars have pulled the same vanishing act, leaving scientists scrambling to explain how a star can skip its own funeral. The leading theory is all about balance, or rather, the lack of it. Normally, when a massive star dies, its core collapses, triggering a shockwave that blasts the outer layers into space. But in some cases, that shockwave might stall, smothered by a flood of neutrinos or swallowed by the star's own gravity. Without the rebound of a supernova, the core keeps collapsing, forming a black hole that devours the star from the inside out. The outer layers, they might simply fall inward, vanishing without a trace. It's stellar death by suffocation, a quiet end for what should have been a cosmic fireworks display. What makes these events so eerie is their stealth. Unlike traditional supernovae, which light up the night sky, failed supernovae leave almost no visible trace. The only hints might be a flicker of infrared light or a sudden absence where a star once shone. Some researchers suspect these phantom deaths could explain why we've observed fewer supernovae than predicted. Black holes might be swallowing stars whole, no explosion required. But here's the twist. Could these failed supernovae be creating a new kind of zombie star? Not the pulsating, radiation-spewing undead we're used to, but something far more sinister, a black hole born in shadow, lurking unseen. Some theories suggest that in rare cases, a dying star might expel just enough material to leave behind a nebula, a ghostly shroud hiding the monster at its heart. Others propose that the black hole's gravity could slowly siphon gas from nearby stars, emitting faint X-rays as it feeds. These wouldn't be the flamboyant, resurrected stars we know, but cosmic vampires, hiding in the dark until hunger forces them to reveal themselves. The hunt for these stealthy remnants is pushing telescopes to their limits. Astronomers are scanning galaxies for sudden disappearances, monitoring stars for telltale flickers, and even listening for gravitational waves, ripples in spacetime that might betray a star's silent collapse. Every new observation chips away at the mystery, revealing just how many ways a star can die or refuse to die in the way we expect. Failed supernovae force us to confront an uncomfortable truth. The universe doesn't always play by the rules. Stars can vanish without a bang, black holes can form in silence, and death doesn't always look the way we think it should. But in that uncertainty lies the thrill of discovery. Because every time a star disappears without explanation, it's not just a mystery. It's an invitation to rewrite the book on how the cosmos works. Cosmic vampirism turns the quiet dance of binary stars into a battle for survival, where one star slowly consumes the other to cheat death. Picture two stars locked in orbit, one a bloated red giant, the other a dense white dwarf or neutron star. Over time, the gravitational pull of the denser object strips gas from its companion, funneling it onto its surface in a swirling accretion disk. This stolen material doesn't just sit there. It compresses under unimaginable pressure, igniting nuclear reactions that can resurrect a dead star or trigger explosions visible across the universe. Take cataclysmic variables, for example. These systems pair a white dwarf with a main sequence star or red giant. As the dwarf siphons hydrogen-rich material, the gas piles up until the temperature and pressure reach a tipping point. Boom. The dwarf's surface erupts in a nova, a thermonuclear blast that can outshine its host star for weeks. But here's the twist. Some of these vampires are repeat offenders. They don't just explode once. They feast, detonate, and repeat like cosmic serial arsonists. Then there are X-ray binaries, where the predator is even more extreme. Imagine a neutron star or black hole orbiting a massive companion, slurping up gas so violently that the infalling matter heats up to millions of degrees, glowing with X-rays. These systems are like celestial diners, with the dead star's gravity shredding its meal into a glowing, high-energy buffet. Some, like Cygnus X1, are so voracious their accretion disks whip particles into jets that blast outward at nearly light speed, carving scars across the cosmos. But what happens when the donor star is finally drained? The aftermath depends on the predator's appetite. A white dwarf might stop at occasional nova outbursts, but if it gorges past a critical limit, about 1.4 times the sun's mass, it collapses in a type supernova, obliterating itself entirely. Neutron stars, on the other hand, can spin faster as they feed, transforming into millisecond pulsars that flicker with precision. And black holes. They just keep growing, their event horizons expanding with every stellar bite. The real tragedy lies with the donor star. Once stripped of too much mass, it can't sustain normal fusion, collapsing into a helium-rich husk or even disintegrating entirely. In some cases, the vampire's gravity distorts its victim into a teardrop shape, a process called lobe overflow, where gas spills uncontrollably toward its predator. It's a slow, cosmic demise, a star shredded not by explosion, but by the relentless pull of its undead partner. Yet these predatory relationships aren't just destructive, they're creative. The stolen material fuels novas, supernovae, and even the synthesis of heavy elements like gold and uranium. Without stellar vampirism, the universe would lack some of its most dazzling phenomena and some of the very atoms that make up our world. So while the donor star's fate may be grim, its sacrifice lights up the cosmos, proving that even in the darkest acts of celestial cannibalism, there's a spark of creation. Imagine a world where the sky is dominated by a cold, dead star, a white dwarf no larger than Earth, yet weighing half as much as the sun. Its pale glow barely lights the surface of a battered planet, one that somehow survived the violent death of its parent star. These aren't just hypothetical scenarios. Astronomers have already discovered exoplanets orbiting stellar corpses, worlds that refuse to perish even as their suns collapsed into zombies. Take PSRB 1257+12, a pulsar with not one but 3 planets circling it. This neutron star spins hundreds of times per second, blasting its surroundings with lethal radiation. Yet somehow these planets endure, charred remnants of a solar system that should have been annihilated when their star went supernova. How did they survive? One theory suggests they're second-generation worlds, formed from the debris of the explosion, forged in fire rather than born in a calm disk. Others propose they're the lone survivors of a once larger family, their siblings vaporized or flung into the void. White dwarfs host even stranger possibilities. In 2020, astronomers spotted a Jupiter-sized planet orbiting WD 1856+534, a white dwarf so dense its gravity would shred a normal planet within hours. Yet this gas giant persists, likely because it migrated outward just as its dying star began shedding its outer layers. The real shock. Some white dwarfs show traces of heavy metals like iron and calcium in their atmospheres, evidence they're actively cannibalizing the remains of rocky planets that strayed too close. But the most tantalizing question isn't just whether planets can survive, it's whether life could cling on in these hellish environments. Pulsar planets are bathed in deadly X-rays and gamma rays, while white dwarf worlds face extreme tidal forces and a slow freeze as their dead star cools. Yet life on Earth has proven remarkably resilient, thriving in deep-sea vents, acidic pools, and even the vacuum of space. Could extremophiles exist on a zombie planet, sheltered deep underground or beneath icy crusts? Some researchers speculate that tidal heating, the same process that keeps Jupiter's moon Europa warm, might maintain liquid water on planets orbiting pulsars, offering a slim chance for life to persist long after its sun has died. The discovery of these undead worlds forces us to rethink the limits of planetary survival. If planets can endure supernovae, pulsar radiation, and the crushing gravity of white dwarfs, then the universe might be far richer in second chances than we ever imagined. And if life can adapt to such extremes, then death might not be the end for entire ecosystems, just another chapter in a story written in starlight and resilience. Pulsar planets exist in the ultimate cosmic danger zone, orbiting a stellar corpse that blasts its surroundings with enough radiation to sterilize a world in seconds. The first of these bizarre worlds was discovered in 1992 around PSRB 1257+12, a pulsar spinning so fast its beams of high-energy particles sweep through space like a lighthouse from hell. At first, astronomers doubted their own findings. How could planets survive the supernova that birthed this neutron star? The answer lies in the ashes of destruction. When a massive star explodes, it doesn't just vanish. It leaves behind a chaotic debris field of heavy elements and shattered remnants. In the case of pulsar planets, scientists believe these worlds are second-generation survivors, forged from the wreckage of the original star system. Picture a swirling disk of supernova leftovers, plutonium, uranium, and other dense metals, slowly clumping together under the pulsar's gravity. Over time, these fragments collide and merge, building rocky or metallic planets in an environment no one thought possible. It's like watching a city rebuild itself from its own rubble after a nuclear blast. But survival here requires extreme adaptations. A typical pulsar planet endures relentless barrages of X-rays and gamma rays, with surface temperatures swinging from scorching heat to deep cold as it tumbles through the pulsar's lethal beams. Some might even be bathed in a perpetual rain of antimatter, created when the star's radiation smashes into stray atoms. Yet against all odds, these worlds persist, their cores possibly molten from tidal forces, their surfaces scoured clean of any atmosphere. The real shocker, there might be stranger varieties lurking out there. Some theorists suggest that pulsars could host diamond planets, worlds so carbon-rich that their interiors crystallize under intense pressure, creating vast subterranean gemstone layers. Others propose the existence of iron planets, where the entire world is essentially a giant ball of compressed metal, forged in the heart of a supernova. These wouldn't just be dead rocks, they'd be cosmic artifacts, the final monuments to a star's catastrophic end. What does this mean for the search for life? While pulsar planets seem inhospitable, nature has a habit of surprising us. Deep beneath an irradiated surface, tidal heating or radioactive decay could maintain pockets of liquid water, shielded from the deadly rays above. Or perhaps life could evolve in ways we can't yet imagine, thriving in environments that defy Earth's rules. One thing's certain: if planets can exist here, they can exist anywhere, proving that death isn't the end of creation, just the start of something far stranger. When a star shrinks into a white dwarf, its planetary system enters a cosmic demolition derby. Some worlds get obliterated, others are sent careening into the void, and a few stubborn survivors cling on like charred witnesses to stellar death. Take WD 1856 plus 534, a white dwarf with a Jupiter-sized planet still orbiting it at breakneck speed. This gas giant shouldn't exist. When its host star ballooned into a red giant, it should have been engulfed. Yet here it is, a cosmic that escaped annihilation by migrating outward just in time. But not all planets are so lucky. Many white dwarfs show eerie metal pollution in their atmospheres, traces of iron, magnesium, and even water vapor. These aren't natural elements of the star. They're the vaporized remains of asteroids and planets that spiraled too close. The process is gruesome. As a white dwarf's gravity shreds a rocky world, the debris forms a glowing disk of molten rock that rains onto the star's surface over. Astronomers call this accretion, a polite term for a stellar corpse slowly cannibalizing its own children. The fate of Earth hangs in this balance. 5 billion years from now, our sun will swell into a red giant, likely swallowing Mercury and Venus. Earth's destiny is less certain. While our planet may escape total engulfment, the sun's violent mass loss could destabilize our orbit, sending us drifting into space or straight into the white dwarf's gravitational shredder. Even if we survive, the aftermath will be bleak. A frozen world orbiting a fading ember, its oceans long boiled away, its surface scoured by solar winds. Yet these apocalyptic scenarios hold scientific gold. By studying metal-polluted white dwarfs, astronomers can perform cosmic autopsies, analyzing the chemical makeup of devoured planets light years away. Some even contain traces of oxygen and nitrogen, hinting at vaporized water-rich worlds. It's as if the universe leaves forensic evidence at every crime scene, and we're just learning to read it. Perhaps most haunting are the white dwarfs with intact debris disks, graveyards where planet formation might be happening in reverse. Dust and rock collide, forming new bodies from old ruins. In this way, death isn't an end but a reset, a chance for new worlds to rise from the ashes of the old. So while Earth's future may be uncertain, one thing's clear: even in stellar death, the cosmos finds ways to rebuild. The sun has been our constant companion for 4.6 billion years, a steady golden orb in the sky, but nothing lasts forever. In about 5 billion years, this familiar star will begin its slow transformation into something far stranger. First, it will bloat into a red giant, swelling so large that its outer layers might engulf Mercury, Venus, and possibly even Earth. But that's just the beginning of its undead evolution. After shedding its outer layers in a shimmering planetary nebula, all that will remain is a dense, Earth-sized ember, a white dwarf, the sun's final form. Unlike massive stars that go out in supernova explosions, our sun isn't destined for a dramatic death. But don't let its quiet fade fool you. Even as a cooling white dwarf, it could exhibit eerie zombie-like behaviors. Imagine a star that's technically dead, no nuclear fusion burning in its core, yet still glowing faintly from residual heat, like a dying ember in a cosmic campfire. Over trillions of years, it will gradually dim, fading into a cold black dwarf, a theoretical state so chilled it would be nearly invisible against the backdrop of space. Yet before that final cold sets in, the sun's white dwarf phase could hold surprises. If any surviving planets or asteroids stray too close, its immense gravity could rip them apart, creating glowing rings of debris, a last macabre feast. Some white dwarfs even show traces of heavy metals in their atmospheres, chemical fingerprints of devoured worlds. Could our own sun, in its afterlife, become a cannibal of its former solar system? There's also the slim chance, though unlikely, that the sun could experience a late-stage resurrection. If a passing star or rogue planet donated fresh hydrogen to its surface, the white dwarf might flare up in a nova, briefly reigniting like a cosmic phoenix. It wouldn't be the dazzling supernova of more massive stars, but even a faint flicker would be a haunting echo of its former brilliance. What legacy will our sun leave behind? Its death will scatter heavier elements forged in its core across the galaxy, seeding future generations of stars and planets. The planets that escape destruction, perhaps a scorched Earth or distant ice giants like Neptune, will orbit a ghostly remnant, their skies lit by a dim, pale disk. And if any life survives, it will witness the ultimate cosmic irony, the star that gave it warmth becoming a cold, dark sentinel in an ever-expanding universe. This future might seem distant, but it's a window into the fate of countless stars like ours. The sun's quiet demise is the rule, not the exception. A reminder that even the most familiar celestial objects are bound by the same universal laws of life, death, and the occasional uncanny afterlife. The oldest stars in the universe are cosmic time capsules, silent witnesses to an era long before planets or even galaxies took shape. These ancient, some nearly as old as the universe itself, carry chemical imprints that tell the story of stellar life and death on a scale we can barely fathom. Unlike younger stars like our sun, which are polluted with heavy elements from generations of supernovae, these primordial relics are almost pure hydrogen and helium, the raw ingredients of the Big Bang. Their atmospheres are pristine libraries, preserving the fingerprints of the very first stellar deaths and the bizarre resurrections that may have followed. Take the star known as HE 1523-0901, discovered in the halo of our Milky Way. At over 13 billion years old, it's one of the most ancient stars ever found. What makes it extraordinary isn't just its age, it's the bizarre cocktail of elements in its atmosphere. Traces of europium, gold, and even uranium lurk there, elements that shouldn't exist in a star this old. The explanation. These heavy metals were forged in the violent deaths of the universe's first stars, titanic behemoths hundreds of times more massive than our sun. When those pioneers exploded, they scattered their guts across space, seeding the next generation of stars with the building blocks of planets and life. But some of these fossils hint at even stranger possibilities. A handful of ultra-old stars show peculiar ratios of elements like carbon and oxygen, patterns that don't match typical supernova models. One theory suggests these anomalies could be the work of zombie stars, white dwarfs or neutron stars that briefly resurrected in the early universe, fusing elements in their death throes before vanishing for good. Imagine a star dying not once but multiple times, each explosion layering the cosmos with new chemistry. It's like finding a prehistoric cave painting where the artist kept returning to add new strokes across. Then there's the mystery of the so-called carbon-enhanced metal-poor stars. These ancient oddballs are rich in carbon but lack heavier elements, a signature that defies conventional stellar evolution. Some astronomers propose they were polluted by the ashes of peculiar supernovae, ones where the dying star's core collapsed directly into a black hole, leaving behind a carbon-rich shell. Others speculate these stars might have been infected by primordial black holes, tiny, hypothetical relics of the Big Bang that consumed their cores and triggered exotic nuclear reactions. Either way, their existence forces us to rewrite the early chapters of cosmic history. The real power of stellar archaeology lies in its ability to turn single points of light into sprawling narratives. By decoding the chemistry of these ancient stars, we're piecing together how the first generations of stellar zombies shaped the universe. Every unusual ratio of elements, every trace of unexpected metals is a clue, a whisper from an era when the cosmos was still figuring out the rules. And as telescopes grow more powerful, we're not just reading these stellar bones. We're listening to them, hearing echoes of explosions that lit up the universe when time itself was young. Dark energy lurks in the empty spaces between galaxies, an invisible hand stretching the cosmos apart at an ever-increasing rate. This mysterious force makes up nearly 70% of the universe's energy content, yet we still don't fully understand its nature, or how it might shape the afterlife of stars. While dark energy's primary role is accelerating cosmic expansion, its subtle influence could ripple through the lives of zombie stars in ways we're only beginning to imagine. Take white dwarfs drifting in the void between galaxies. As dark energy pushes galaxies farther apart, these stellar remnants could find themselves increasingly isolated, cut off from the gas and dust needed to reignite as novas or supernovae. Without companion stars to feed on, their chances of resurrection dwindle. The universe's expansion might literally starve these undead stars of their second acts, leaving them to cool in solitude for eternity. But dark energy's reach could extend beyond mere isolation. Some theories suggest it might alter the very fabric of spacetime on quantum scales, subtly tweaking the conditions that govern stellar collapse and rebirth. Imagine a neutron star teetering on the edge of becoming a black hole. Could dark energy's repulsive force tip the balance, either delaying its final collapse or triggering it prematurely? The math is speculative, but the implications are staggering. Even the faintest influence on gravitational interactions could rewrite the rules for how stars die, and how some refuse to stay dead. Then there's the cosmic horizon problem. As dark energy accelerates expansion, distant galaxies will eventually vanish from view, their light stretched beyond. For zombie stars in those regions, their flickering resurrections, novas, pulsar glitches, magnetar flares might become invisible to future civilizations. It's a haunting thought, entire populations of undead stars, their final struggles lost to the expanding dark, like embers winking out in an endless night. Yet dark energy might also create opportunities for rebirth. In regions where expansion stretches matter thin, rare collisions between isolated white dwarfs or neutron stars could become even more violent, sparking unprecedented supernovae or gravitational wave events. The universe's acceleration doesn't just pull things apart, it reshuffles the deck, creating new chances for cosmic resurrection in the most unexpected places. The deeper we probe these questions, the clearer it becomes. Dark energy doesn't just shape the universe's future. It might quietly sculpt the life cycles of its most persistent inhabitants, the stars that refuse to die. And that's the real mystery, not just what dark energy is, but how it intertwines with the universe's most defiant survivors, bending their fates in ways we're only starting to glimpse. Multiverse theories flip the script on everything we think we know about zombie stars. In our universe, these undead celestial bodies already bend the rules. White dwarfs stealing life from companions, neutron stars spinning faster than kitchen blenders, black holes belching radiation like cosmic indigestion. But what if the laws of physics weren't universal constants? What if, in some alternate reality, gravity worked differently or nuclear forces had another strength? The possibilities for stellar resurrection become infinitely stranger. Picture a universe where dark energy doesn't just accelerate expansion. It crackles through space like lightning, reigniting dead stars with every pulse. Or one where the strong nuclear force is weaker, allowing neutron stars to spontaneously unravel in bursts of quark-gluon plasma, only to reform hours later like cosmic jigsaw puzzles. In these alternate realities, zombie stars might not be rare anomalies. They could be the norm, with stellar corpses flickering in and out of existence like lights in a haunted house. Some theoretical models suggest universes where matter behaves in ways we'd find impossible. Imagine a white dwarf that doesn't just siphon material from a companion, but teleports it through microscopic wormholes, appearing to explode randomly without any visible fuel source. Or a magnetar whose magnetic field loops back in time, causing it to happen before the crust actually cracks, a literal case of the effect preceding the cause. These aren't just thought experiments, they're stress tests for our understanding of physics, showing how fragile our rules might be when stretched across the multiverse. Even more mind-bending is the idea that some universes might have zombie stars as their primary celestial bodies. If the cosmological constants allowed for slower fusion rates, stars could naturally pulse between life and death, dimming and reigniting in cycles lasting centuries. Civilizations in those realities might consider our stable, long-lived stars the true cosmic oddities. Or perhaps in a brain world scenario, where our universe is just one membrane floating in higher dimensional space, stellar remnants could leak energy into adjacent dimensions, appearing to resurrect when they're actually siphoning power from unseen neighbors. While these ideas remain speculative, they serve a crucial purpose, reminding us that our universe's version of physics isn't the only possible script. Every time we study a pulsar's precise ticks or decode the remnants of a type supernova, we're glimpsing one variation of stellar death and rebirth. Out there in the multiverse's infinite tapestry, other stars might be dying in ways we can't even name, and returning in forms beyond our wildest imagination. The lesson isn't just about alternate realities, it's about humility. Our zombie stars are strange enough, but the cosmos always has stranger tales waiting in the wings. Detecting zombie stars requires a cosmic game of hide-and-seek, where astronomers wield tools far beyond ordinary telescopes. Take white dwarfs. These faint embers glow with leftover heat rather than active fusion, making them incredibly dim compared to living stars. To spot them, scientists rely on sensitive instruments that detect subtle shifts in ultraviolet or infrared light, signatures invisible to human eyes. The Space Telescope has cataloged thousands this way, revealing ghostly remnants lurking in what seemed like empty patches of sky. But the real breakthroughs come when these dead stars betray their presence through violent outbursts. A sudden flare in X-ray or gamma-ray wavelengths often signals a white dwarf stealing matter from its neighbor, its resurrection written in high-energy radiation. Radio telescopes play an entirely different role in hunting undead stars. Pulsars, spinning neutron stars that beam radio waves like cosmic lighthouses, were first discovered through their rhythmic pulses. These signals are so precise that slight variations can reveal mind-bending details. A pulsar wobbling from an orbiting planet, or slowing down as it drags spacetime around it like a spoon through honey. Arrays like the Very Large Telescope in Chile or the upcoming Square Kilometer Array will amplify this ability, mapping the gravitational warps around these dense corpses with unprecedented clarity. Then there's the James Space Telescope, a game-changer for studying stellar zombies. Its infrared eyes peer through cosmic dust to spot the faintest white dwarfs, while its spectrographs dissect the chemical fingerprints of material they've consumed. Recently, detected surprising amounts of carbon and oxygen around a white dwarf, evidence it might have shredded and ingested a rocky planet rich in these elements. This isn't just observation, it's celestial forensics, reconstructing violent events from atomic clues. But the future holds even wilder possibilities. Next-generation gravitational wave detectors could catch the moment two neutron stars collide, revealing how their merger births new elements or even black holes. Meanwhile, projects like the observatory will scan the entire sky nightly, hunting for zombie stars that flare unpredictably, dead one moment, blazing back to life the next. The most thrilling prospect, finding something entirely unexpected. Magnetars with magnetic fields strong enough to distort atoms from light years away, white dwarfs erupting in ways that defy current models, or neutron stars harboring exotic states of matter we've only theorized. Every time we improve our tools, the universe reminds us, the strangest resurrections are still waiting to be discovered. The night sky isn't just for professional astronomers. It's a vast frontier where anyone with curiosity and a sharp eye can make groundbreaking discoveries. Some of the most thrilling finds in zombie star research have come from amateur stargazers, people who spend their nights scanning the cosmos with backyard telescopes or even just their laptops. 2008, a high school teacher named Caroline Moore spotted a supernova in a nearby galaxy, becoming the youngest person at the time to discover one. Then there's the amateur astronomer from Argentina who captured the exact moment a star flared back to life in a distant galaxy, his footage providing crucial data on how white dwarfs steal matter from their companions. These aren't outliers. They're proof that the universe doesn't care about credentials when it hands out cosmic revelations. Projects like Galaxy Zoo and the American Association of Variable Star Observers have turned citizen science into a powerhouse for uncovering stellar anomalies. Picture this: you're scrolling through telescope images online, tagging strange patterns or sudden bright spots. One of those blips could be a pulsar glitching, a white dwarf erupting, or even a never-before-seen type of stellar resurrection. In 2021, volunteers sifting through data from the Space Telescope helped identify a bizarre binary system where a white dwarf was actively cannibalizing its partner, a discovery that made headlines in astrophysics journals. The tools are simpler than you'd think. Some projects require nothing more than a smartphone and a knack for spotting patterns. But what if you want to go beyond classifying data? Backyard astronomers with modest telescopes regularly contribute to monitoring known zombie stars. Take the case of recurrent novae, white dwarfs that explode repeatedly every few decades. Professionals can't watch them constantly, so amateurs fill the gaps, logging subtle changes in brightness that might hint at an impending eruption. Some even use homemade spectrographs to analyze the chemical makeup of these stars, tracking how much helium or carbon they're stealing from their neighbors. The key is consistency. While professionals chase the big discoveries, it's often the patient, dedicated amateurs who notice when something's off, a flicker where there shouldn't be one, or a star that's dimming too fast. The best part, you don't need to wait for a eureka moment to contribute. Simply joining a community like the AAVSO or participating in a project adds to a collective effort, like a cosmic search party combing the darkness for clues. Every logged observation, every flagged anomaly, helps build a clearer picture of how stars cheat death. And who knows, the next time a magnetar unleashes or a white dwarf erupts in an unexpected galaxy, it might be your data that helps scientists decode what's really going on. The universe is full of mysteries, and sometimes, all it takes to solve one is a curious mind and the willingness to look up. Hollywood has a knack for turning cosmic phenomena into blockbuster spectacles, and zombie stars are no exception. These celestial undead have slithered their way into sci-fi lore as symbols of ultimate cosmic dread, sometimes portrayed accurately, other times twisted beyond recognition. Take the 2014 film Interstellar, where a dying star system harbors a massive black hole named Gargantua. While the movie nails the mind-bending physics of time dilation near a black hole, it takes creative liberties with the visuals, presenting an accretion disk glowing like a neon halo. In reality, the radiation near such an object would vaporize anything long before a ship could skim its edges. Then there's the paradox, where a rogue energy experiment accidentally teleports a space station near a pulsar. The film depicts the star as a crackling, malevolent force, an exaggeration, but not entirely baseless. Real pulsars do emit deadly radiation beams, and their magnetic fields could fry electronics from thousands of miles away. Yet the movie glosses over the most fascinating part: the pulsar's precise rhythm, a trait that real scientists use to navigate spacecraft in deep space. Literature often digs deeper into the eerie symbolism of stellar resurrection. In a Revelation space series, neutron stars become tools for an ancient alien civilization, their gravitational waves harnessed as cosmic Morse code. It's a poetic twist on real science. We do use pulsar signals to map the galaxy, but amps up the stakes by turning these dead stars into weapons. Even HP flirted with the idea in the out of space, where a meteorite's alien energy drains life from its surroundings, mirroring the way real white dwarfs leach matter from companion stars. But pop culture's biggest miss might be the portrayal of zombie stars as singular, apocalyptic threats. In reality, their danger and their beauty lies in their diversity. A white dwarf supernova is a predictable cosmic yardstick, not a random doomsday event. Magnetars don't actively hunt ships like some interstellar jaws. Their deadly flares are rare and distant. And while black holes are terrifying, their horror is subtle, a slow, not a sudden vortex sucking entire fleets. What fiction gets right, though, is the existential all these objects inspire. From Doctor Who's sentient star in the rings to the zombified sun in Sunshine, storytellers tap into a primal fear. The universe is vast, uncaring, and full of things that refuse to die quietly. That's the real power of zombie stars. They're not just science. They're reminders that the cosmos operates on rules we're still deciphering, where death is just another state of being. And that's a truth far stranger than any screenplay. Imagine a future where humanity doesn't just observe the cosmos, we reshape it. Picture scientists tinkering with the core of a dying star, reigniting it like a celestial mechanic, or engineers nudging a black hole's orbit, harvesting its energy to power civilizations. These scenarios sound like science fiction, but with the rapid pace of technological advancement, they might one day enter the realm of possibility. And that raises a profound question. Just because we could resurrect or manipulate stars, should we? The ethical dilemmas here are as vast as space itself. On one hand, stellar resurrection could be the ultimate act of cosmic stewardship. Take white dwarfs. If we could safely trigger their supernovae in controlled bursts, we might distribute heavy elements like iron and gold to star-forming regions, enriching future generations of planets. Or consider redirecting rogue black holes away from inhabited systems, acting as galactic shepherds to prevent catastrophe. These interventions could be framed as altruistic, even necessary, for the long-term survival of intelligent life. But the risks are equally staggering. Tinkering with stellar physics could unleash unintended chain reactions. A miscalculation in reigniting a neutron star might produce lethal gamma-ray bursts, sterilizing nearby worlds. Harvesting energy from a black hole's accretion disk could destabilize its orbit, sending it careening toward populated systems. And who gets to decide which stars live or die? The potential for misuse, whether as weapons or tools of cosmic colonialism, looms large. Would we repeat Earth's history of exploitation, this time on a galactic scale? Then there's the philosophical weight of playing God with celestial bodies. Stars and black holes aren't just resources, they're the architects of the universe. Tampering with their life cycles could alter the very fabric of reality, erasing natural phenomena that future civilizations might rely on for survival or knowledge. Imagine a distant alien culture depending on the pulse of a millisecond pulsar for navigation, only to find it silenced by human hands. Our actions could echo across, with consequences we can't foresee. Yet perhaps the most unsettling question isn't about capability, but humility. The universe has operated for 13.8 billion years without our input. What hubris does it take to assume we'd improve its design? Indigenous cultures on Earth often speak of sacred landscapes, Might the cosmos, too, hold intangible value beyond its utility? Even if we develop the technology to resurrect stars, the greatest challenge might be recognizing when to leave them be. This isn't just hypothetical navel-gazing. These debates lay the groundwork for how we approach lesser cosmic interventions today. From deflecting asteroids to drafting space mining regulations, every decision sets a precedent. If we can't agree on ethical boundaries now, how will we navigate the staggering power of stellar engineering later? The answers might shape not just humanity's future, but the fate of the universe itself. One thing's certain, the stars have died and reborn without us for eons. The real test begins when we ask whether they should do so with us. The next decade promises to peel back the veil on zombie stars like never before, thanks to a fleet of advanced missions designed to probe these cosmic anomalies in ways we've only dreamed of. Leading the charge is LISA, the Laser Interferometer Space Antenna, set to launch in the mid-2030s. Unlike ground-based gravitational wave detectors, LISA's trio of spacecraft will orbit the Sun, forming a million-kilometer-wide triangle capable of sensing the faintest ripples in spacetime. This isn't just an upgrade, it's a game-changer. Imagine catching the gravitational whispers of white dwarfs spiraling toward collision, or the tremor of a Magnetars from across the galaxy. LISA could reveal how often these undead stars merge, how their violent dances warp spacetime, and even uncover entirely new classes of stellar remnants we've yet to imagine. Then there's Athena, the advanced telescope for high-energy astrophysics, slated to launch in the late 2030s. While LISA listens to the universe's vibrations, Athena will stare directly into the heart of cosmic violence. Its X-ray vision will dissect the superheated debris around neutron stars and black holes, mapping the furious winds of material they tear from companions. Picture this, a white dwarf caught in the act of stealing gas from a neighboring star, its accretion disk glowing white-hot under Athena's gaze. Or a Magnetar mid-quake, its crust cracking like eggshell under magnetic pressures so intense they distort atoms. Athena's observations could settle long-standing debates, like whether some type supernovae come from colliding white dwarfs or solo stars pushed past their limits, by spotting the chemical fingerprints left behind in their wake. But the revolution isn't limited to massive flagship missions. Smaller projects like the probe, launching in 2024, will scan the sky for sudden X-ray flares, the telltale screams of neutron stars feeding or black holes awakening. Meanwhile, the Square Kilometer Array radio telescope, coming online in stages this decade, will turn pulsars into cosmic laboratories. By tracking subtle hiccups in their spins, it could detect gravitational waves from supermassive black hole mergers or even phantom energy from cosmic strings, theoretical defects in spacetime itself. The most tantalizing possibilities lie in the unexpected. Every time we've built a telescope with unprecedented sensitivity, from to JWST, we've stumbled upon phenomena that rewrite textbooks. Could LISA detect a neutron star collapsing into a quark star, a hypothetical state denser than anything we know? Might Athena spot a white dwarf pulsating like a zombie heart, its eruptions following patterns we can't yet explain? And what if these missions uncover stellar remnants defying classification altogether? Objects that aren't quite neutron stars, not quite black holes, but something stranger in between. One thing's certain, the golden age of zombie star research is just beginning. As these missions come online, they won't just fill in gaps in our knowledge, they'll tear open new chapters in astrophysics. From decoding the birth cries of black holes to witnessing stellar resurrections in real time, the cosmos is about to get a lot louder. And for those listening closely, the revelations waiting in the static could redefine what we thought we knew about life, death, and the undead in the cosmic graveyard. For all our cosmic detective work, zombie stars remain some of the universe's most reluctant witnesses. We've pieced together their stories from flickering X-rays and gravitational tremors, but crucial chapters are still missing. Take objects, those bizarre hybrids where a neutron star orbits inside a red giant. Decades after their prediction, we've only found a handful of candidates, and even those resist confirmation. Their chemical fingerprints hint at unimaginable nuclear alchemy happening deep within. But without catching one in the act of formation or destruction, we're like archaeologists guessing at an entire civilization from a single shard of pottery. Then there's the enigma of magnetar flares. We know these ultramagnetic neutron stars occasionally crack under pressure, unleashing bursts of energy that outshine galaxies. But why do some erupt like clockwork while others sleep for centuries? The triggers could involve quantum fractures in their crusts or instabilities in their magnetic fields, or something entirely unforeseen. It's like trying to predict earthquakes without knowing if the ground beneath us is rock, jelly, or liquid metal. Even our best understood undead stars harbor secrets. Type supernovae, those cosmic measuring sticks, still argue amongst themselves. Most align with our models of white dwarfs stealing mass, but outliers explode earlier or brighter than expected, as if something, dark matter, exotic particles, is tampering with their internal clocks. And what about the rogue white dwarfs drifting alone through space? Conventional wisdom says they need companions to resurrect, yet a few have flared up unexpectedly, like embers sparking without visible fuel. Perhaps most humbling are the gaps we haven't even recognized yet. Before pulsars were discovered in 1967, no one imagined dead stars could spin hundreds of times per second while beaming radiation like cosmic lighthouses. Before magnetars were identified in 1998, magnetic fields a quadrillion times Earth seemed impossible. What other forms of stellar resurrection lurk out there, defying our current playbook? Could black holes, those supposed endpoints, have resurrection mechanisms we've yet to conceive? This isn't failure, it's the heartbeat of science. Every unanswered question about zombie stars is an invitation to look deeper, build better tools, and question assumptions. The universe didn't promise us all its secrets at once. Those flickering stellar corpses with their irregular pulses and cryptic outbursts aren't just mysteries, they're mentors, teaching us how much wonder remains in the dark. Zombie stars force us to rewrite the cosmic rulebook, revealing a universe far stranger than we ever imagined. These celestial undead aren't just scientific curiosities, they're active participants in shaping the cosmos, from seeding galaxies with heavy elements to bending spacetime with their gravity. Consider the humble white dwarf, a fading ember one moment, a supernova the next, or neutron stars spinning faster than a jet turbine while beaming radiation across. Even black holes, those supposed endpoints of existence, might slowly leak particles back into the universe through Hawking radiation. Every one of these phenomena shatters our neat classifications of life and death, proving that in the grand theater of the cosmos, finality is an illusion. What makes these stellar resurrections truly remarkable isn't just their defiance of expectations. It's what they teach us about reality's fundamental fabric. When a magnetar's crust cracks under magnetic pressures strong enough to distort atoms, we glimpse physics pushed beyond laboratory extremes. When colliding neutron stars spray gold and platinum across space, we witness the universe's alchemy in action. These events aren't just happening light years away, they're the reason your wedding ring exists, why your electronics work, why life itself had the building blocks to emerge. The calcium in your bones likely came from a white dwarf's final explosion billions of years before Earth formed. The frontier of discovery keeps expanding. Next-generation telescopes might spot quark stars, hypothetical objects even denser than neutron stars, or catch a white dwarf resurrecting without a stellar companion, hinting at dark matter's invisible hand. Gravitational wave detectors could reveal black holes merging with neutron stars, a catastrophic marriage that would warp spacetime itself. And who's to say we've found every variety of stellar undead? The universe operated for billions of years before we started watching. Entire categories of zombie stars might be lurking in the darkness, waiting to upend our models once more. This isn't just astronomy, it's a profound lesson in humility. For all our equations and theories, the cosmos keeps surprising us. A dead star isn't an end, but a transformation. A black hole isn't just a grave, but possibly a gateway. Every time we point our telescopes skyward, we're not just observing the universe's history, we're witnessing its endless capacity for reinvention. So when you next look at the night sky, remember, those twinkling lights aren't all alive in the traditional sense, but very few are truly dead. The universe doesn't do endings, only changes. And in that infinite dance of destruction and rebirth, who knows what other resurrections are waiting to be found? The search continues, and the cosmos never runs out of wonders.